Hey, it's Friday. Gotta get down on Friday. Everybody's looking forward to the weekend. Gotta get down on Friday, yeah? You? How about you? Yeah, we've been talking all week about a little bit about genes, gene switches, epigenetics. We've been talking about embryos and stem cells and stuff like that. And today we're concentrating on embryos. And where it's leading us to is the idea of like gene switches being evidence of shared evolutionary history, right? Because when we look at embryos, we see that gene switches get turned on at certain times. And we looked at certain different species, you see that we actually share the same switches, get turned on but they get turned on at different times. So you wind up growing a little bit different. So the different differences between organisms isn't always DNA genes. You might have the same genes, just different switches for those genes. If that makes sense. If it doesn't, maybe it will soon as we look at embryos today.
All right.
Hey now.
Mr. Kovacs class. It's Mr. Kovacs class. You might learn a ton. It's Mr. Kovacs class.
It's interesting too.
It's Mr. Kovacs class.
And he's super cool.
It's Mr. Kovacs class.
Yeah, we're talking about embryos. Embryos, as we know, a pretty early developmental stage for an organism. And most organisms that are multicellular have an embryonic stage. And the embryonic stage, what defines it is that the cells are figuring out what they need to do, right? It's almost like this is the stage where it's building the framework for the organism, right? And then once you're done putting the framework in, you can make the different parts bigger or smaller, whatever you need to do, more complex. But once you get the framework down, that's the embryo. And, before the embryo, of course, right, we had zygote, and it splits, it goes through mitosis, and then finally a ball of cells, we call them morula, right? And then once that morula becomes a big ball of cells, it's ready to stick to the uterus, and mom is pregnant, we call that a blastocyst, right? And it attaches to the uterus, and what you have, of course, are cells on the inside and the outside of this ball of cells, right? The inside cells are going to become the endoderm, or the inside of that organism, right? And the outside cells are going to become, actually usually in the placental mammal, the placenta, or part of the amniotic sac, if that's something like that, something. But in mammals, it would be placental, right? And so this is what's going to differentiate into an organism. And then once it starts to differentiate, we call it an embryo, right? An embryo is differentiated. In this embryo, in this x-ray, you can see, right, that this embryo started already growing its backbone and its spine and forelimbs and front limbs, and it's probably put a heart in there. Its brain is starting to develop. Eyes are starting to develop, right? Yeah, and what we know about organisms is that, especially like if you look at placental mammals, we all have we go through the same steps of embryo. So it's almost like we turn on the same gene switches at the same time, right? And then once those switches are turned on, we grow at different rates, and that's what makes, body parts different from each other. If you compare, let's say a pig to a sheep to an elephant, okay, right? An elephant's nose cells are gonna grow a lot longer than the nose cells of a pig, let's say, right? They're gonna grow for longer. That means the switch will be turned on earlier in order to grow that for a while, right? But a lot of if you think about a lot of the structures found inside organisms, they're the same. They're just different in size. Like the heart of a pig is built the same as the heart of yours, but it's just a little bit different size. The heart of a cat is the same as yours. It's much smaller, right? And so, again, differences between organisms have to do with switches, when they go on and when they turn off. So we're going to look at embryos today. Embryos are fascinating because they tell the story of development, right? And they tell the story of how to build an organism. It's kind of like pre-programmed. DNA is like the programmed step of instruction guide of what switches to turn on when in order to start making certain proteins in certain places. And that's what builds organisms. We use embryos a lot too as an example of evolutionary similarities. Because if you look at organisms, the more closely related they are, and you look at their embryos, the more difficult it is to determine which embryo is whose, right? I mean, that's going to be an activity we'll do in class today. All right, so right, you look at the embryos of two different, right? These are two different dogs, actually. All right, two different dogs, two different breeds of dogs. You can see that at certain stages of their embryos, they are basically identical, but as they develop, they throw switches at different times, and they develop subtle differences between the two, right? And then you wind up with two dogs. They're the same species, but they'll have very big phenotypic differences because of when the switches are thrown. So yeah, I get excited about talking about embryos and embryonic development, and we're gonna look at some embryos in class today. And again, we use embryos as an example of evidence that organisms share common ancestry, right? Because of the genes that they have and the switches that turn on the genes when those switches activate, right? The more closely related two organisms are, the more genes they have in common and the more switches they have in common. Hopefully that makes sense. All right, so developmentally, you develop similar patterns. All right, we'll talk about that more in class. Let's enjoy our Friday. Got to get down with Friday and working for the weekend. Yeah, fun, party, yeah.